When a solute dissolves in a solvent, we actually get an equilibrium process. So remember when we talked about water evaporating? We talked about how the water molecules that near the surface might have enough kinetic energy to escape, then they get into the gas state, and especially if this is a closed container, they're going to bounce around up there, but eventually they're going to collide with the water and get stuck again. And so we've got this balance between evaporation and condensation. Similar thing happens with dissolving a solute. At first, the rate of dissolving is much higher than recrystallizing because there's nothing out there to recrystallize. But as the concentration of the dissolved solute increases, then the rate of recrystallization will increase, and eventually we end up with a dynamic equilibrium. So just like the water evaporating and condensing came to like an agreement, right? So the amount of water in the gas state is constant, even though it's different molecules. There's this turnover happening. The concentration is the same. And so that also happens with solids dissolving in liquids. We'll have the salt dissolving, but then sodium and chloride ions can run into each other and reform the solid. So this is those ideas illustrated. So here we got the chunk of salt in the beaker of water, and initially the only thing that can happen is this dissolves because there's nothing out here that can recrystallize. So we've got this dissolving, and as this dissolves and forms these little, ion dipole force guys out here, now some of these can come back and recrystallize. But dissolving is still happening at a higher rate. As the concentration of dissolved stuff increases, then the rate of recrystallizing increases, and at some point these become equal to each other. So it looks like nothing's happening, but actually salt is dissolving and recrystallizing continuously. A saturated solution is one where we have the solvent, and there's enough solute there that it's reached the solubility limit, and there's some solid sitting on the bottom. And so we're going to get that dynamic equilibrium with the solid solute. So we've come to this point where the rate of dissolving and the rate of recrystallization are equal to each other. If we add more solute to that solution, it will not dissolve. We can't raise the concentration anymore. An unsaturated solution has less than that equilibrium amount of solute. So if we add more solute, then it will dissolve because it has not reached equilibrium yet. And then there's the possibility of a supersaturated solution. These are unusual. They are very unstable. So here, the solution contains more than the equilibrium amount of solute, which seems impossible, right? The way supersaturated solutions are generally formed is that you form them at a high temperature because the solute is more soluble at high temperatures. We'll talk about that in a minute. And you let it cool down very slowly, and the solute doesn't realize that, oh, wait a minute, I'm too concentrated, I should precipitate out. It's a little bit like the Bugs Bunny Roadrunner cartoons. They're always running off cliffs, aren't they? They're running real fast, and they run off the cliff, and they keep going in midair. And they don't fall until they realize that they ran off the cliff, right? It's ridiculous. Completely tears apart physics, right? But that's how the cartoons are. So a supersaturated solution is a little bit like Roadrunner, who ran off the cliff but hasn't realized it yet. But as soon as you point that out to him, he's going to fall. So this supersaturated solution has to be treated very, very carefully. And so here, something as simple as just taking a glass stir rod and touching the surface says, hey, you've got too much in there. You should be precipitating. Oh, okay. You know, Roadrunner falls, right? And yet they never die. And so the recrystallization will begin. Not all substances will form supersaturated solutions. So I'm going to show you a couple videos here. So that's a supersaturated solution. I stuck a rod in there and it begins to crystallize. Isn't that cool? So that's the dissolved solute just crystallizing really fast. And the one that they usually do these demos with is sodium acetate because it just does this so nicely.
In a series of experiments carried out between 1908 and 19...
Yeah, we really didn't want to do that. And this is another one where they're just kind of having fun with this. So they made supersaturated solutions, and now they're just kind of messing around with them. So stick some toothpicks in there. You can get these, like pom-pom crystals to form. This is an exothermic reaction. So the temperature there was 52 degrees instead of 25. So sometimes this is called hot ice because it looks like it's water freezing, but it's getting warmer. This is kind of this sort of wet solid. And so you make little sandcastles with this stuff because as soon as it hits, it's like, oh, wait a minute, I'm supposed to be precipitating, and it does. It becomes a solid. And it's just going to continue up into the beaker. This video was obviously made before video stabilization was common on cell phones. It was jiggling all over the place. It's like the word is spreading through the solution. Hey, we're supposed to precipitate, and the word goes on, and then it precipitates.
Pampers, the #1 pediatrician recommend.
Love those ads. So, if you remind me during lab, I believe I can do that for you. Make a solution. Not the second one, because that's an awful lot of work making all of that, but the first one, where we make a supersaturated solution and then we watch it crystallize. But you have to remind me because I will forget. So this is showing the relationship between the solubility of these different substances and the temperature. So for most ionic compounds, they are more soluble at higher temperatures. So if we look at potassium nitrate, we see down here at 10 degrees, you're only going to get about 20 grams of it to dissolve in 100 grams of water. But if you raise the temperature to, say, 40 degrees, now a little over 60 grams will dissolve. And this is how the supersaturated solution is formed. You get a saturated solution formed at a higher temperature. So you get it all to dissolve, and then you let it cool down slowly without disturbing it, or even thinking negative thoughts about it. It's very sensitive. And as it cools down, it just doesn't realize that it's supposed to precipitate. As it cools down, it's like, okay, we're way over dissolved here. And so then as soon as it is disturbed, it will precipitate out. So we can see that the relationship here between solubility and temperature is linear for some things. It's exponential for others. For sodium chloride, it's actually relatively constant. Sodium chloride is very soluble in water, but heating it up just doesn't help that much. And then there's some weird ones that are less soluble at high temperatures. Those are kind of weird. So recrystallization is what happens after the ions have dissolved, and then they're coming back and reforming the solid. And this can be a really useful technique for purifying a solid. So if you make a solid during an experiment, like we made zinc iodide, right? It was dissolved in methanol. We had the zinc and the iodide, and then we heated off the methanol, and we got this like crusty, whitish mess at the bottom of the beaker, right? Well, there could be impurities in that. What you can do to purify it is you can dissolve it again at a high temperature and then allow it to cool slowly. And as the crystals reform slowly, they're going to reject impurities because they want to make that particular crystal lattice that substance makes. And so if there's like a sodium ion that's getting in there, that's going to get in the way. And so that's going to have time to redissolve and other correct things come in and recrystallize. So you can purify and get some beautiful crystals that way. That's how rock candy is formed. You make a solution of water and sugar at an elevated temperature, and you let it cool down slowly, and these big, beautiful sugar crystals will form. That's something you can try at home, but you should look up some instructions because I remember trying that as a kid, and I didn't know what I was doing because I'd never had chemistry, and it didn't work out, right? It has to be really concentrated sugar solution at a high temperature, right? And then let it cool slowly, and you can form rock candy. So temperature affects the solubility of liquids. Solubility of solids and liquids. It also affects the solubility of gases. Solutions of gases in water are actually quite common. Here we have soda being poured into glasses. This is a soda that was refrigerated before it was poured, and this one was not refrigerated. And so we see all this foaming happening. What causes that? Well, the soda contains dissolved carbon dioxide. And when you pour it out, the dissolved carbon dioxide begins to come out of solution, and that's the little bubbles. So here, at a cold temperature, the solubility of the gas is greater than at a warmer temperature. So it's the opposite trend. Gases are less soluble at high temperature, whereas solids are more soluble at high temperature. So when you pour the warm soda, the carbon dioxide will come out faster. So if you want to pour your root beer and not make a mess, it's better to refrigerate it first. This is another little experiment you could try. Put 2 glasses of soda on the counter, and one of them started out cold and one of them started out warm, right? Actually, you need to keep the cold one cold. So you take the cold one, you put it in the refrigerator, and you leave the warm one out on the counter. And come back the next day and taste them. The one in the refrigerator will still have some carbonation in it. It'll still have some fizz in it. But the one that was sitting out on the counter will probably be flat or almost flat. Right? There's no carbon dioxide left in there. because at this higher temperature, the carbon dioxide is less soluble. This has implications for aquatic life because oxygen levels are lower in warm lakes and rivers. That's why, if you're going to have fish in an aquarium, it's important that you keep the aquarium water at the correct temperature so that they have the amount of oxygen dissolved in the water that they were meant to have or that they need. Pressure has a big effect on the solubility of gases. So gas will be more soluble if the pressure of the gas above the liquid is higher. And so this is why, soda is sold in tightly sealed containers. So here we have a can of soda, and it's not completely full all the way to the top. There's a little bit of, sometimes called head space, and that's carbon dioxide under pressure. When you open the can and it makes that psst sound, that's pressurized CO2 escaping. The pressure has been lowered here, and now that the pressure is lower, the solution, the carbon dioxide begins to come out of solution because the solubility is lower without that pressure. Does anybody have any questions about that? You can see this happen in like a 2-liter bottle. When you open it, before you do anything to it, you start to see bubbles coming up, right? Those bubbles, that's your soda starting to go flat. It begins that process as soon as you open the container. So here we have an equilibrium situation where we have carbon dioxide up here, and carbon dioxide is dissolved in the water, and so some of it is escaping and some of it is getting trapped again. If we push down on this plunger and increase this pressure, that's the same as increasing the concentration, right? Because it's a smaller volume. And so now the carbon dioxide molecules are going to run into this solution, just like condensation. It's going to run into this more frequently, and so the rate of dissolving will increase while we still have the gas coming out of solution. And so now more of it will dissolve, and it'll keep doing that until it comes to a new equilibrium condition. So the cans, bottles of soda are pressurized to increase the solubility of carbon dioxide in the water. We can quantify the relationship between gas solubility and the partial pressure, and this is known as Henry's law. So Henry's law says that the solubility of a gas, and that's usually measured in moles per liter, is equal to a constant times the partial pressure of the gas. And so here's a table giving the Henry's law constants, and these are molarity per atmospheres. Talking in the hallway. This is definitely not something you'd memorize. Henry's law is used in very limited situations. This is not a chemistry big deal thing. Determine the solubility of oxygen in water at 25 degrees Celsius exposed to air at 1 atmosphere. Assume a partial pressure for oxygen of 0.21 atmospheres. So here we're looking at the relationship between the solubility of a gas and its partial pressure. So that's Henry's law. So let's go back and remind ourselves what Henry's law is. Solubility is this constant times the pressure. Now I forgot what oxygen, forgot what gas we were talking about. So we need this constant. For oxygen, it's 1.3 times 10 to the minus 3. And this is true at 25 degrees Celsius, which the problem is also at 25. So we need that 1.3 times 10 to the minus 3. So the Henry's law constant here is 1.3 times 10 to the minus 3, and that's moles per liter per atmosphere. So we've got this temperature, we've got partial pressure of oxygen, we have the pressure of air, and we are asked to find the solubility of oxygen. So Henry's law says that the solubility, here is the solubility of oxygen, is going to equal the Henry's law constant times the partial pressure of oxygen. So we were given a total pressure for the air of 1 atmosphere, and we were also given a partial pressure for the oxygen. So it's this partial pressure that we want to use. So the solubility for oxygen there is going to be the Henry's law constant times the partial pressure. And we see that the units of atmosphere cancel out. And this gives me 2.73 times 10 to the minus 4 moles per liter. Which should have 2 sig figs, so 2.7 times 10 to the minus 4 moles per liter is the concentration of oxygen in water. Any questions?